So thanks everybody for coming today. We will discuss a bit about the exercise of the chapter 4, the classification. As you have coming through the exercise, this chapter, the difficult curve kind of up a lot because in this chapter will come through a lot of algebra, especially when the case comes to the multiple predictor or the multinomial case of our classifier. So I find this chapter quite hard to interpret. So in today's class, maybe we can solve some questions together if there's any questions that I cannot explain clearly. So first of all, I think maybe it would be helpful for us to review a little bit about the model we've lived through in this chapter. So can everybody see my PDF on the screen, right? Okay, sure. So a little bit review about the comparison between the models we've come through. The first one is logistic, the LDA, QDA, the discriminant analysis, and the naive Bayes, and the k-nearest neighbors. So in the book, the author discussed the 6 scenarios. The first 3 is that our Bayes decision boundary is linear, and the other 3 is that the scenario means that the boundary is non-linear. So in this case, all 6 cases have 2 predictors. And in the scenario 1, it gives that the training observations, there are training observations, and the classification is a binary classification. So and our observations within each class, they are uncorrelated. So it means that the observations across each class is independent. And so in this case, we can say in this figure that given that the underlying data is random distributed and across each class they are dependent. So the decision boundary is also linear. So the LDA, the linear discriminant analysis, and the logistic analysis performs the best. They have the best performance. Is that we can it is because the LDA and the logistic they all assume that the decision boundary is linear. And the more flexible solutions, such as the KNN and the QDA, they on the other hand, they do not capture the best performance. So we can say that it is not that our model is more flexible, the better. It depends on what the underlying data set it is, what the underlying data set is. So in the second scenario, the condition change to that the predictors they have a bit of correlations between each other. So in this case, we can see that the naive Bayes, which assumes that the underlying data sets they are independent between each other, the naive Bayes the performance drops a lot. So it means that this is a very important assumption if we want to conduct the naive Bayes analysis, naive Bayes modeling. And in the third case, the underlying distribution is changed from the normal distribution to t-distribution, and the observations is 15 per class. It means that the observation is kind of large, that we do not worry about the small sample case. So in this case, the in that the sample is large enough, so the t-distribution resembles the normal distribution, but it has a tendency to yield more extreme points. That is, more points that are far from the mean. So in that setting, the decision line was still linear, and then so fit into the logistic regression framework. But the setup violates the assumption of the LDA. So in this situation, the logistic performs the best, but followed by the LDA, and we can see that naive Bayes is the least best performance in this setting. So so from the first 3 settings, we venture through into the last 3 scenarios where the underlying decision boundary is non-linear, So in scenario 4, we still assume that they are from a normal distribution, and but there is some correlation between predictors, and then also that because there is a two-class, but the correlation across two classes is different also. So in this setup, the QDA assumption performs the best because the underlying variance across each class is not equal. So in this scenario, the QDA is the best model we can choose. And in the scenario 5, we assume that there's a normal distribution and the predictors are independent between each other. And the response is sampled from a logistic function, which means that the underlying distribution is not parametric. It's not parametric. So which is the relationship between the response and the predictor is not parametric. So there is a non-linear decision boundary. And in this case, the most flexible model, the KNN with the neighbor, the K more than 1 performs the best. But on the other hand, the KNN with the K equals 1 gives the worst result. So this shows that the fact that even the data is a complex non-linear relationship, a non-parametric method such as the KNN can still give a poor result. So we have to determine which level of K is the best. So in the last scenario, this case is same as the scenario 3 with a different covariance, with a different variance between each class. So in this case, but there is an assumption that the sample size is very small. So in this case, naive Bayes performs very well. So a little bit of a summary here. We can see that this is something that we can refer to when we do our modeling in terms of each classification problem. So here's a 5 minutes review about all these models, and then we will come into our exercise today. So everyone can see my web page about the exercise. Okay, cool. So the first part is about the conceptual problem. This sort of problems help us to dive into the mathematical foundation of all these models. So it needs a little bit of algebra. And the first question is that about the logistic function. To prove that the logistic function represent the logic representation of the logistic regression model are equivalent. So we can see the function here is the 4.2 and the 4.3. We can review a little bit of what it looks like. I guess, yeah, the 4.2 and the 4.3 function is here. The first is the logistic function. We model the probability of x of we predict the x belong to a certain classifier of is this function. We model it as this one, and then we will do a logic transformation, which is compute the odds of this quantity. So we have to confirm that these two equations are equivalent. So from the algebra side, there's a bit of algebra. If you guys found this difficult, please feel free to come out. I'm not good at to explain it clearly, so let's just skip through it. And then in terms that I have found it that involves a bit of the fraction and the logarithm. So that's the part of it. That's the gist of it. And then the next question is talked about in the text of classifying an observation to class for which this part function, I remember is that decision function is the largest. It's equivalent to classifying an equation to the class for which the other function is largest. And to prove that this is the case, in other words, under the assumption that the observation in the case class are drawn from a normal distribution, and the Bayes classifier assigns the observation to the class for which the discriminant function is maximized. So we return to the 4.12 and the 4.13. The 4.12 is a largest function of a given x of a probability of a probability of a classify observation as a k, given that the underlying predictor equals x, and it's divided by the by a baseline case. So this larger function is largely equal to, it's basically equal to the logistic function that we modeled before, and we have to prove that this function is equal to the 4.13, which is the the softmax coding of this function. So first, we see that 4.12 is the thing like that. The one in the denominator is the priori probability of the probability of classifier A or class K, and then the second term is the underlying the density function of the normal distribution, and this denominator is the total probability of P is the total probability of the Bayes theorem. So their discriminant function is that the case that we classify K to be 1, and we classify the K to be 2, is that in these two cases, when the probability of classifying these two cases equal, that is our discriminant function, and we can get discriminant function. We can see that it is a first degree function, so it's a linear function basically, and you can treat other terms like constant in this case because when in terms of each class we have a constant, the mu the mean value, and the constant pi of the prior probability of k. So in terms of this case, since the underlying variance, since the variance is constant, then we can construct this function in this way, and then we have to maximize to maximize our probability of classify the observation as a k. So we get this function to maximizing the log of it, and finally we still get we still get a linear function behind of it. So the gist of it is that if we choose a baseline case to compare one class and the other class, the result would be equal to a softmax coding, which classifies observation to k regardless of what the baseline is. So this is the underlying logic of this question. And in the question 3, the model changes to the QDA model, which means that the variance across each class is different from each other. So in this question, it just considers the simple case when there's only one predictor. So suppose that we have k classes in this case, and that if an observation belongs to the case class, then the predictor comes from a one-dimensional normal distribution. So that simplifies our problem a lot. And recall that the density function for one-dimensional normal distribution is given as this function. So prove that in this case, the Bayes classifier is nonlinear. In other words, it's a quadratic function of our discriminant function. So as we proved, we have to prove that in this case, the underlying function is largely the same as before, but we have to pay attention to the variance in the case, because the linear discriminant model assumes that the underlying variance across each class is all the same. They are all equal. They are homoscedasticity across each class. But in the quadratic situation, the variance is not equal. So we have to do a bit of matrix or kind of complex algebra computing about across each case. And and we have to find the maximize the probability of we classify things as a K. So the underlying after some calculation, the underlying function is here with the x as the predictor, and we found that this function and other things as a constant. We found that in this function, the x is a quadratic form. It has a power to it. It has a second power to it. So unlike in the linear situation, it is not independent of hk. So the underlying function is a quadratic form. So we after come through the discriminant case, we into the fourth question, we talk about the k-nearest neighbor, which is the most flexible models across all these models. So this question asks that when the number of features, the predictors is large, there tends to be a deterioration in the performance of the KNN. That's we talked a little bit in our first chapter that when the feature is small, when the feature is too large, it's large even than the case. So this table would be wider. So it be much wider. In this case, we will suffer the curse of dimensionality. So and the other local approaches that perform prediction using only observations that are near the test of the observation for which a prediction must be made. So this phenomenon is called the curse of dimensionality, and it ties into the fact that non-parametric approaches often perform poorly when the P is large. So we investigate this curse. So first of all, suppose that we have a set of observations and each measurement on P equals 1, and we assume that the X is uniformly distributed on 0 to 1, and associated with each observation is a response value, so that we wish to predict the test observations response using only observations that are within 10% of the range. That is, if we choose a point that is 0.5, that is the in the half path in the left side there's a 0.005, and the left side is 0.5. So the range is that 0.45 to the 0.55 in that range, and the nearest neighbor close to the x. So for instance, that if the x is equal to 0.6, so the range is the 15.5 to the 16.5. So for values that we use just 10% of the observations, near the point that we're interested of. So similar to this value, we have found the distance between each case that is nearest to the point that we're interested of. So in this one, I'm confused about the result because I just computed that it's just because the case is that it's just it's a two-dimensional. It's just on the line. It's one-dimensional. So if we shrink if we constrain the distance, if constrain the range just 10% around the observation, I think the area that we want to catch on the line is also 10% around each observation, but the result gets is 9.75. I don't know why the result here. I don't know if someone get the same result as me, 10%. So you can see that
that's
in
not
my
something I could figure out.
Okay, cool. So in my case, I just see that the thing is distributed on a normally line, and that's a line from the 0 to 1. So we want to find the 10% range around the 0.6. So which is this case because the range is on a line. So if the length is 10%, the area we want to capture around the point is also 10% on this line. So I think it is a corresponding 10% nearest neighbor, but the result, the solution gives that 6.75. So I actually do not know why. So and another searched online from other solutions from other people, they comes the solution same as me. So I'm quite confused about this. But we will figure it out later. And then in the next case, we increase our dimensionality to 2, which is we consider that there's two features. That is, we can construct the XY plane of the X1 as the X plane, as the X1 X-axis, and X2 as the Y-axis. So in this case, the area we want to catch is not a line, but a plane. It's 2D, it's a 2D plane. So in this case, we still assume that they are uniformly distributed across each axis. But we want, we also want to capture the nearest 10% range of our points of interest. So in this case, we will assume that X1, the point of interest is 0.6 and 0.35. So in this case, we want to catch the area around this point, because it is a line. So we can know that the long of it and the wide of it and the way multiply them together to get a quadratic form. So in this case, the area, the coverage of if we just choose each line we capture at the length of 0.5, the average we can capture shrinks exponentially. It almost shrinks to the 10% of the range that we can capture when the case is on the line, is just one-dimensional. So we can see there's a huge loss in this situation when we get more features we have to predict. So now let's suppose that we have an observation that there's 100 features that we want to capture. So the area that we can capture exponentially decrease to a point nearly to 0. So in other words, if we still just to set the range on each dimension as 0.1, the overall range that we can capture, the overall volume or overall space that we can capture in this 100-dimensional case, we almost capture nothing. So in this case, our result will be when we bias, it almost can only predict the same case. So from all these parts, we can see that the biggest drawback of the KNN way our feature is large is that there are fewer training observations near our test observation. We can find nothing other than the test one, and if other than the training one. If we want to use this result to predict to predict on the test case, we might get almost every case that we will predict a wrong result. So in this case, as the P increases, the fraction of observations near any given point rapidly approach to 0. It exponentially decreases. So for instance, if you use 15% of the nearest observation for each P, with P equals 10, the only 0 points to the power of 10, that nearest 0.1% of points that are near that you can capture. So now suppose that we want to know if we want to capture the 10% space near the point in a p-dimensional hypercube centered around this test observation. So what length of each side of this hypercube that we have to capture in our modeling? So we assume that it's a hypercube with the length on each axis the same. So we can just reverse this. We can just reverse this function, because this function tells us what space, what volume that we captured. We can just reverse it back to get how much length we have to capture in order to capture the 10% space around this thing, around this observation. So when the P is 1, clearly the length is just 0.1, because there's no reduction in the curve of dimensionality. But if we increase the p to 2, so in this case, the square length have to equal the 0.1. That is the area we want to capture. So the length of each side have to be the square root of 0.5, which is 0.32, which is almost 3 times larger than the one that we use in the one-dimensional case. And if this p increases, the length is this function. So if in order to, in the case of n equals 100, and then we have to capture, because the overall length on each side is 1, we have captured the 98% of length of each x to reach the area, reach the space that we want to capture. It means that almost every space, the space, every part of the space that we have to consider into to help us to get just a 10% nearest the range. So it means that the KN case it performs very bad when the features is huge. So this case talks about the curse of dimensionality, and they use the mathematical function to tell us about the foundation behind it. And the five questions talked about the difference between the linear and the quadratic discriminant analysis. So if the underlying the Bayes decision boundary is linear, do we expect the LDA and the QDA perform better on the training side or the test set? So the first is the training set. Because the QDA is a more flexible model, it can capture more residues, more flexibility of the model. So in the training side, the QDA is always perform better than the LDA. But since the underlying Bayes decision boundary is linear, so if you turn our model into the test set, in fact, the LDA would perform better because it can predict more accurate than the QDA. But if the underlying boundary is non-linear, we can expect that the QDA performs better on the training set and the test set as well. So, but in general, as the sample case n increases, do we expect the test prediction accuracy of the QDA relative to the LDA to improve or incline or be changed? So as the n increases, the sample size increases, we would expect the prediction accuracy of the QDA improve as there is more data to feed to the subtle effect in the data, which means that the the ratio of a given number of a parameter to the sample size decreases. So the influence of the features decreases, so leading to induction in the variance of estimation within each class. So so review a little bit about the function of the test error. We can see the test error is constructed by two things. One is the bias of our estimation. The second is the variance of the estimation. So as the sample size increases, the variance decreases. It compensates. It offsets a lot. It makes the reduction of the bias by the QDA function more economic, more efficient in our production. So the overall test accuracy of the QDA relative to the LDA will improve. So no matter, I guess if the underlying Bayes decision boundary is linear, it'll be even better. So the last question is that even if the Bayes decision boundary for a given problem is linear, or would probably achieve a superior test error rate using the QDA rather than the LDA, because the QDA is flexible enough to model a linear decision boundary. I think that the answer is false, and because the QDA tend to overfit, so which leads to a poorer test performance, as we talked before, when the underlying decision boundary is linear. So so the sixth question is that we suppose we collect the data. It's kind of like an example. With there are the two predictors of this case. The one is the hours studied of each student. of this group of students in the class. And second is their undergrad GPA. And we want to predict if the student will receive an A based on these two predictors. And we use logistic regression with and use two coefficients. The first one is the intercept coefficient is -6, and the second one corresponds to the first predictor is 0.5 or 0.5. 0.05, and the second one corresponds to the undergrad GPA, which is 1, which means that these two predictors is tend to positively correlated to the underlying proportion of a student receiving an A in this class. So the logistic function is here, and we can reverse that into in the logistic function here, and we can reverse this order by taking a logarithm of it, and then we can use this function to get a prediction of the probability that the student will receive an A if he studied 14 hours per week and have a 3.5 undergrad GPA. So it's the same as if we want to have a 0.5 chance, which is our decision boundary. It's like our decision boundary. So we will find the case that where the probability is 0.5, take this case back to our foundation, we will find that the hours the student have to study is 15 hours per week. So the next question, it talks about the prediction of the given stock. Well, whether they will issue a dividend this year is a binary classification with yes and no. So it's based on the X, the last year's percent profit, and we have some prior information about it, the mean value of the last year percent profit, and the mean value of X for companies that issue the dividends was that the mean value of this group, that the group where the companies will issue a dividend was issued a dividend last year, and their mean value is 10, and where the mean value of the other group is 0. So in addition, the variance, of course, each set they are equal. So in this case, we would use LDA that might be the best model. And finally, we have a prior probability of whether a company will issue a dividend. The probability of that is the 0.8. And so we can take that into our function, and we assume that's a normal distribution. And we want to predict that the given is actually equals 4, whether the probability of the company will issue the dividends in the next year. So in this case, we use the LDA function, and follow that function line. We can compute this result. We can just use our R to compute that for us. And the next question is talked about the k-nearest mean, and it talks about the another set, the training set and the test set, split the data set in equally sized two sets, and then try out two different classification procedures. First, we use a logistic function that we can get error rate when it fits on the training data. And if we fit this model on the test data, the error rate comes to the 13%. And next, we use the one nearest neighbors, which is the most flexible nearest model, and get an average rate of just 18%. But we have to know that it's the average rate. It's average over the both test and the training rate. And we know that the first nearest neighbors is the most flexible because it's just focused on the most nearest neighbors of our observations. So we can just assume that the test rate, the error rate of this model on the training set is equal to 0. So if we assume that it's equal to 0, but the average rate across two sets is 18%. So it means that the test error rate on the training data set has to be the 36% is average from it. So But the real error rate that we're interested of is the one on the test set. So in this case, the logistic regression outperforms the first near neighborhood, 1 year neighbors. So the sixth question talks about R, the R function, as we define here. The R function is here, and we know the probability, and we know the R. We can reverse calculate the probability of the case. And if we increase the probability, if we have, the probability is 0.16, and we can calculate the odds of it. And the one thing we have to mention is that the odds function is a line that starts from 0 and to infinitely bigger value. It's not as the probability which only ranges from 0 to 1. And the question 10 is a bit more it asks us to derive expression for this log, which is the compare the case we're interested of and compare the baseline case and get the log odds. And in the case where the p equal greater than 1, so it is a multiple case, and the mean is and so that the mean for each class mu k is a p-dimensional vector. It means that we have to use a matrix calculation here, and they share the covariance. So it is an LDA case, not an unequal variance case. So in this case, we just say the p equals 1. So it simplifies a lot, and we have to derive this function. This function is the same one that derived on the book, but of some hand calculation here, we can see that the underlying function is here. It is still a first degree function. It's not quadratic, so the underlying thing is still linear. And we can see that AK and BK is a constant in this case. And the next question, we derive the function to QDA case where the variance across each class is not equal, so it'd be kind of more complex. And I derived it myself, but I'm not sure if it's right, and I handwritten it, but so I cannot show it here. So maybe you guys can try it out, or refer to some linear algebra book to try to figure out. And then the next question talks about the log odds, and it involves a bit of the calculation. The most important part of this question, I think, is that we compare the results of the case that we just compare it. The case that we just compare it with a baseline case, and the second case is that softmax the formulation. We can find that the result of these two formulations is largely the same. So, but their coefficients will be different. So we have to pay attention of it when we choose the different formulation of our problem. So next three questions is about the applied. We have to use our data set to build our model. I guess everyone have more experience on R than me. So I think this part I just walk a little bit through our problem, and maybe everyone will get their results or have their different ways of reaching the solution. So first question is we use the weekly data set, which is a data set that is similarly to the S-market data set we used before, but it has but it turns the daily returns into a weekly returns, and it begins at from 1919 to 2010. And the summary of this case, we can see that there's the thing that we want to predict is the direction, whether this stock will go up or down. And then there are a bit of prediction here with the year as the first prediction of which year it is. And then this 5 leg is the time lag of each, and the time lag of each of their returns across the week. and the volume of each day or week, I don't know. I'm not quite remember that it traded, and the today's performance of the stock. And the solution construct the correlation plots across each feature. We can see that the volume is largely correlated to the. I'm not sure which one. I think it's largely correlated to the. Let me check back to my results.
Marker sheet show high correlation.
Yeah, high correlation, but yeah, it's safe correlation. It's correlated with year, right? It's safe correlated. Sorry about that. Correctly. Yeah. Oh, yeah. Just to show these metrics. Yeah, so we can see that there's a high correlation between the volume and the year. So as the year from the 1990 to the 2010, the volume increases as the year goes on, and there's not much correlation between other predictors. So the volume is strongly, they expand in the next sentence. Yeah, this is strongly positively correlated with the year, but other correlations are weak. And we can see also that there is some self correlation, some collinearity between some of the predictors. So in the second question, we perform a logistic regression. In this case, use the GLM function and this as the response and the other things as the predictor. And use this data as familiar, choose the binomial case because the response we want to predict is a binary classification. And then we summarize the feed. And we can see that other than the intercept and lag2, the other case is not that significant that we can agree, and we can reject the null hypothesis that there's no relation between the predictor and the response, and so the next two is significant, and then we can reduce our model to just use the lag2 as the predictor. And the third question is compute the confusion matrix. And I found that the argument function of combining the prediction and our data that I want to predict, and this function is quite useful when we want to know the confusion matrix. So, for example, if we use this command, we can get this confusion matrix. We can see that the overall prediction, the overall accurate rate is not that good, and this function can just tell us what's the accuracy rate. It's just 0.156. It's not that great, and the result is the same. So overall fraction of the correct is just 0.6, 0.56. And then we refine our model to just use the predictor that is significant as a lag2, and we can see that the overall accuracy increased a little bit. And this is the case of the logistic regression. And if we turn to the LDA, which is this function, use the LDA, and we predict that, we can see their results the same. So that means this is because the underlying distribution of each they are largely normal. We can assume that the underlying distribution of each predictor is basically normally distributed. So So we can use the LDA as a special case of a logistic regression in this case. But if we turn to the LDA, the result deteriorates. It means that maybe the underlying decision boundary is linear, so the linear function performs better here. And if we use the most flexible function here, it performs even better. So the accuracy rate is just 0.5. It means that we can just predict 1 out of 2 prediction that we can get a right predict, get a true prediction. And if we use a naive Bayes, which assumes that the underlying distribution, the underlying relationship between each predictors and they're independent, we can see that the performance is not that good. Because we can return to our data, we can see that there is some correlation between each predictor in this case. So I think the linear case, the logistic regression, and the LDA is the best in terms of this case. So they are best performing one, and we can make a lot of experiments with different combination or use the different value of k. I don't know if there's a more handy function of it, or there's some package that we can do it quite handy way, because that is a lot of hard work or the kind of dirty work of it. But if there's any package, I think there will be there's a lot of efficiency here. So as we can see from this plot, that when the y is the accuracy of our prediction, and the x is the k we choose, you can see that when k reaches 26 or 13, between this line, the accuracy which is the biggest, and it's not that bigger than the LDA. So maybe the more polynomial function, the LDA and the logistic regression, we can choose as that as our best regression model, as our best prediction model here. So this is the largely the workflow of our analysis of the prediction of the classification case, and the next 3 questions, they're largely the same. We have to first perform the EDA of the exploratory data analysis of the underlying data to know there's some relationship. For example, if there's a collinearity between each predictor, or if the underlying distribution of each predictor is normal, and the other things that the variance across each class is the same, is equal or unequal. So first, in this data set, we can conduct some data transformation. First is that we create a binary variable that whether the miles per gallon is greater than the median value, or it's lower than that one. And by create that, we turned out our prediction problem into a binary classification to predict whether it's greater than the median or it's lower than median. And then we do some graphically exploratory analysis of our underlying data set, that we can see that the cylinder is a categorical predictor, orange is a categorical predictor, and the other things is that continuous. And we can see that the acceleration is kind of same like a linear distribution, but we have to perform some hypothesis test of it. And the other thing is kind of largely skewed to the right. And then we can perform the relationship between each predictor and our response. And we can use the box plot here to stay more clear of our relationship. For example, we classify the case as the false and true of MPG1 and their corresponding distribution of their predictor. So I think there's a lot of techniques in terms of the EDA, and everyone and each one has their own method to reach a kind of heuristic understanding of the underlying data set. So that depends on each one. So in this question, we talked about how to split the data into a training set and test set, because that we had to make a cross validation. So in this case, the author classified the data set by the 2/3, that is almost 66% as the training data set, and the other 33% as the test set. I found an interesting thing here because I choose the 75% as our training set and the other 25% as the test set. And I use the same modeling technique, and the result, they are largely different. Not that different, but there's some difference. So it means that the level we choose, how we split our data, it matters a little bit, or even bigger, matters bigger. And also my result is kind of confusing, is that if I choose the 75%, I receive the same result in terms of each model. My prediction of each model, the LDA, the logistic, and the LDA, the QDA, and even the logistic, they are all the same. Their performance is all the same. I don't know why, but if you classify it as just 2/3, just 66%, it have a slightly difference, but not that different a lot. So and if you use naive Bayes, they have a different result here. So we have so if we want to figure out, that's why we have to dive deeper into the foundation of this model. We have to know why this model can get this result, to figure out which one is the best. So that needs a bit of, so we have to learn a lot. Yeah. And this is the same case that we use the continuous learning to figure out which K is the best to get the lowest test error. But in this case, the K is he chose the K as the 32, right? I don't know why it's 32, because pretend this plot, it seems that the lowest error appears here, but not here. So I don't know why it choose 32 as the best K. Yeah. And then the other questions about the function, how to write a function in R. And the last question is kind of self-analysis of this data set. So it's largely the same workflow. So I want to dive deeper into the detail of this question, but I want to see that a biggest thing that we have to do in our exploratory phase is that we have to make some hypothesis tests of the underlying distribution and the underlying relationship between each predictor to kind of guide them, to kind of give a guidance for us to choose which model that we want to choose and which predictor that we want to include in our model, and even how to transform our predictor into a form that might to get a better result. So we have to review back of some of our statistical knowledge about the hypothesis test, about the test between different means, about the test of the nonlinearity. So if we have some knowledge about the data set, we can do better of our modeling procedure rather than just try and error. I think it takes a lot of time. So that's today's discussion of this chapter exercise. So I don't know if there's any question about it.
Sounds good. If it was me, if I was doing this in practice, I'd probably use all the packages in tidy models.
Yeah.
Because they make it easier to test many models at once.
Yeah, I use this chapter to practice how to use the tidy model, because I do not use tidy model before. I found the tidy model is kind of, it just formalized the workflow. It asks you to first to make the specification, and then to draw a model, and then choose some recipe. So, but if you just to solve this exercise, you can just use the simple function here. Yeah. And the other thing that I want to add is that I don't know if you know the other book from the same author. It's called The Element of the Statistical Learning. It's the same. It's the book written by the same author. It's this book, The Elements of the Statistical Learning. It dives a lot more deeper than the introduction book, which explains a lot about the underlying the mathematical logic behind of it. And my plan is that I can go through the introduction book, and then if I learn some more mathematical knowledge and have a more solid knowledge about the underlying mathematical things, I will dive deeper into this book. But at this time, I found it hard to comprehend. It's a lot more difficult than the introduction book. Yeah. So the time is come to the 1 o'clock. I don't know if you guys have more questions, but today is my talking here. Thanks for you guys coming here, talk a bit about this chapter of classification. Yeah.
Thank you for reviewing.
Yeah, thank you. That was